Hello and welcome to this episode of Physical Attraction. This week we're going to do something a little bit different in a break from our normal series, and I'm going to read to you a modified version of an article that I wrote for my website, the website that I write for, Singularity Hub, all about AI, artificial intelligence, and how we can get insights from the psychology of children to develop better algorithms. It's called What 4-Year-Olds Can Do That AI Can't. Instead of trying to produce a program to simulate the adult mind, why not try to produce one that simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. That's what Alan Turing wrote in his groundbreaking paper in 1950, Computing Machinery and Intelligence. And by doing so, he laid the groundwork for generations of machine learning scientists to follow. Yet, despite all of these increasingly impressive specialised applications in image recognition, solving problems and so on, and breathless predictions about where AI might go next, we are in fact still some distance from programs that can simulate any mind, even one much less complex than a human's. Even if you take something like the nematode worm, which has the most small number of neurons of any creature that we've studied that we know about, this is still an open challenge, and indeed there's a project called Open Worm that is attempting to simulate the brain of the nematode worm in full. So we're a long, long way from getting anywhere near creating a mind like a human mind. Perhaps the key came in what Turing said next in his paper in 1950. Our hope is that there is so little mechanism in the child brain that something like it can easily be programmed. Now this seems in hindsight naive to think that there's a very little amount of mechanism in the child brain. Moravec's paradox applies. Things that seem like the height of human intellect, like a good stimulating game of chess, are easy for machines when they can easily be broken down into mathematics, but simple tasks like walking around, picking things up and so on can be extremely difficult. If you think about it in a particular way, human intelligence and machine intelligence can often seem to be worlds apart. You or I would struggle to multiply together two 6-digit numbers, but calculators and computers can do this in an instant. Yet to replicate most of the things that we all take for granted, things like moving around in our environments, navigating, finding the appropriate grip to pick up an object, this requires machines and computer intelligence many thousands of hours of training, a significant amount of computational power, and a huge amount of data to even begin to process. It's the equivalent of doing billions of those nasty multiplications for them, yet we all take it for granted. Similarly, you might not know all that much about the laws of physics, although hopefully listening to the show is helping a little bit. I'm fabulously inept at every single sport that exists, surprising no one. But when Joss Butler smashes a cricket ball over mid-wicket, or Serena Williams hits a perfect backhand winner down the line, neither of them are actually doing the explicit calculations of Newtonian physics, trajectories, and integrating the differential equations in their heads. In the same way, we don't seem to explicitly crunch all of the numbers necessary to do everything that we can do. Or at least, we don't have access to that same raw calculation power to actually, perform calculations. Estimates for the actual computational power of the human brain are varied, and since it is a computation that's almost different in kind and very difficult to categorise, it probably makes more sense to go the other way. Rather than saying how many megaflops or how many megabytes is a human brain, its hard drive, its processing power and so on, you're better off saying, okay, let's start with these computer metrics and determine how much computer power we need to create a computer that could do everything that a brain could do. And of course, by some metrics, the human brain is still more powerful than our best supercomputers. And in fact, it is this long childhood that we have that has an awful lot to do with that. In some ways, you can see the human strategy as an evolutionary gamble. Humans are vulnerable for an extraordinarily long time. It takes years and years before we can fend for ourselves and reproduce, longer than the lifespans of many animals. And during this time, we need constant care. We can't feed ourselves for many of these years. A huge proportion of the food that other humans give us during this time, during our childhood and development, is devoted to developing the brain. In fact, they've done studies, careful biological studies, that have demonstrated that somewhere between 60 and 80% of the energy that's absorbed through food by young humans goes into the brain in early childhood, which leaves the body to develop much more slowly, and it leaves us vulnerable for a much longer time. But it's clear that this prolonged childhood is the key to the intelligence. Amongst dolphins, amongst humans and other primates, even amongst the smartest birds, corvids like rooks or crows, the species with the longest childhoods and infancies tend to be the most intelligent because they have that extra time to develop. There's a good example in the world of birds. Crows take 1 to 2 years to mature, and they can use tools and solve abstract reasoning problems in experiments. In some ways, they're the smartest animals that we know about, aside from humans. Chickens take 1 to 2 weeks to mature, and they can basically just peck at the ground. they're practically as intelligent after their heads are cut off as they were before. So clearly the prolonged childhood development allows for a greater final intelligence. And it's this evolutionary gamble, requiring us to go through this protracted phase of learning where we're essentially completely dependent on other, that has paid off. And, well, it's made it all possible. Your mileage may vary, of course, on whether we do good things with the education that we have in childhood. But if children are our template for the simplest general human level intelligence we might program, then surely it does make sense for AI researchers to study the many millions of existing examples. If it's going to be much, much easier to program something that can learn and develop and get better over time, rather than trying to instill all of human knowledge into a single computer, then surely it makes sense for these AI researchers to look at what makes children such good learners. And this is precisely what Professor Alison Gopnik and her team at Berkeley do. They seek to answer how sophisticated are children as learners? Where are children still outperforming the best algorithms, and how do they do it? Some of their answers were outlined in a recent talk at the International Conference on Machine Learning. The first and most obvious difference between 4-year-olds and our best algorithms is that children are extremely good at generalizing from a small set of examples. Machine learning algorithms are the opposite. They can extract structure from huge datasets that no human could ever process. No human could ever read through all of the data that goes into some of these image datasets that are used by ImageNet and things like this. But generally you do need large amounts of training data for good performance. On the other hand, if you have a child, you can show them one picture of a cat or a dog, and they'll always recognise a cat or a dog. They won't need to churn through many, many billions of different datasets. And in fact, we know from our studies of how these machine learning algorithms work that they seem to pick up on particular features that aren't picked up on by humans. So for example, if I were to show you a picture of a polar bear, and then I showed you a picture of an outline of a polar bear, versus, say, an outline of a giraffe, or an outline of a human, or an outline of any other animal, you'd be able to recognise the animal and put it into categories just based on the outline. But the machine learning algorithms would struggle unless they'd been trained specifically with labelled outlines. That is to say, they can't take away the detail, the picture, the colour, the texture of the image. It's these things that they actually use to determine what they think a polar bear, or a dog, or a cat, or an owl is, for example. And indeed, furthermore, you can actually show that what they do is they focus on tiny bits of an image and look at sort of the adjacent pixels and how they change. So if you completely scramble an image such that you have, say, divided up into 20 different squares and then mix those all around, like one of those puzzles you did as a kid, it wouldn't be easy for a human to necessarily recognise what the original image was, especially if they'd not seen it before, but it barely affects the performance of the machine at all, because the machine learning algorithm, at least in this particular study, wasn't really looking at the big picture. It wasn't recognising the animal so much as it was recognising gradients of colour, light, texture and so on in the picture itself. Now when you train these algorithms, this training data usually has to be labelled, although unsupervised learning approaches are now starting to make progress. In other words, there's often a strong supervisory signal, which you either code into the algorithm so that it has some way of knowing that it's performing well on a task, or indeed into the dataset, where every bit of data that's read reinforces some particular statistical association about the data. So every data is labelled and the machine can learn from every data. And all of this serves to consistently reinforce the algorithm as it improves at its task. But children can actually learn to perform generally on a very wide variety of tasks with very little supervision, and they can generalise what they've learned to new situations they've never seen before. Even in image recognition, where machine learning has made great strides and done really well recently, algorithms require a large set of images before they can confidently distinguish objects. Children may only need one. And of course, the ultimate difference between children and our average machine learning algorithms is once an algorithm has been trained to perform a particular task, it may even be superhuman at that task, but it won't be able to do anything else. AlphaGo, the Go program that has effectively beaten all humans at Go, which was considered an extremely complicated game, is not going to be able to write you a sonnet or recognise a picture of a cat. In fact, there's very few algorithms of any kind that can be generally trained in that way. So once you've created these intelligences, you've sort of created these very narrow, specialised intelligences. But children, they don't seem to be set up by these same restrictions. They can perform reasonably well at a vast array of tasks. So how is any of this achieved? Professor Gopnik and others argue that children have abstract generative models, that explain how the world works. In other words, children have imagination, and they can use that imagination to ask themselves abstract questions like, if I touch this sharp pin, what will happen? And then from very small datasets and experiences, they can anticipate the solution. In doing so, they are correctly inferring the relationship between cause and effect from experience. Children know that the reason that this object will prick them unless handled with care is because it's pointy, and not because it's silver or because they found it in the kitchen. This may sound like common sense, but being able to make this kind of causal inference from small datasets is still hard for algorithms to do, especially across such a wide range of situations. Generative models are increasingly being employed by AI researchers. After all, the best way to show that you really understand the structure and rules of a dataset is to produce examples that obey those rules. If you want to show that you know what a polar bear looks like, draw me a polar bear. Such neural networks can compress hundreds of gigabytes of image data into hundreds of megabytes of statistical parameter weights, and learn to produce images that look like the dataset. In this way, they learn something of the statistics of how this particular data works. But to do what children can, and generalise with generative models, imagining all kinds of different situations and trying to reason out how they would work, is just computationally infeasible, according to Gopnik. But this is far from the only trick that children have up their sleeve when it comes to learning. Experiments from Professor Gopnik's lab show that children have well-developed Bayesian reasoning abilities. Now, Bayes' theorem, if you're unfamiliar with it, is all about how you can assimilate and add new information into your assessment of what's likely to be true. It's about updating your prior knowledge based on some new piece of evidence and other circumstances that you need to take into account. So, for example, finding an unfamiliar pair of underwear in your partner's car might be a worrying sign. But if you know that they work in dry cleaning and use the car to transport lost clothes, you might be less concerned. In other words, if you trust your partner, for example, your prior might be that they probably aren't cheating on you, and that this is probably explainable away by something else, and then the probability that they are cheating, given that you found this thing, it's conditional on what else you know about the situation. Scientists at Berkeley present children with logical puzzles, such as machines that can be activated by placing different types of blocks onto different receivers, or complicated toys that require a certain sequence of actions to light up and make music. Pull this lever, press this button, twist this switch, that sort of thing. You can see how this sort of puzzle sets you up for Bayesian reasoning, because as you're observing someone playing with a toy, or as you're experimenting with the toy yourself, you're learning more and more about the rules that govern the system. And, depending on how you believe the system to work, and what the new information that you're getting about the system is, it should update your balance of probabilities for how the machine works. When they're given several examples, a small dataset of demonstrations of the toy, for example, they can often infer the rules behind how the new system works, even from the ages of 3 or 4. They might not necessarily be able to explain in language how it works, but even at this stage, they're perfectly capable of working out the toy. So these are Bayesian problems. The children are assimilating the new information to help them understand the universal rules. And they're causal problems too. There's causal inference. The children are understanding what causes what to happen. When the system isn't explained, the children's inherent curiosity leads them to experimenting with these systems, testing different combinations of actions and blocks to quickly infer the rules behind how they work. And this is one of the key aspects of how children learn. They're very active learners. They get into things, they interact with their environments, they gather data, and they update their priors based on what they've learned. And indeed, it's the curiosity of the children that actually allows them to outperform adults in certain circumstances, because they can find strategies that adults never find. For example, in one experiment they introduce an incentive structure, points that can be gained or lost depending on your actions, and stickers or candy in reward for solving the problem. Once these incentive structures are in place and there's a point system that's being scored on, the adults tend to become conservative and risk-averse. But the children don't really care about the points all that much. They're mostly concerned with understanding how the system works, and hence they deploy riskier strategies. So, for example, they might try out more combinations of blocks. They might try out more ways of handling the toy. They're not necessarily just going to copy what they've seen already, but instead they'll experiment, because they're more interested in doing something new than doing something that they know will work. And consequently, if they find some weird way of doing things that's actually way more efficient than what the adults would do that sort of seems to be the most common sense direct answer, they will often succeed. And if the experiment is designed in this way, then they'll succeed where the adults will fail. So curiosity may kill the cat, but in the right situation, this can allow the children to win the game by identifying the rules that adults might miss because they're avoiding any actions that they think may result in punishment. This research shows not only the innate intelligence of children and the value of curiosity, but it also touches on classic problems in algorithm design. The explore-exploit problem is well known in machine learning. Put simply, if you only have a certain amount of resources, time, computational ability, etc., are you better off searching for new strategies, or simply taking the path that seems to lead most obviously to you winning? Children favour exploration over exploitation. This is how they learn, through play and experimentation with their surroundings, through keen observation and through asking as many questions as they can. As we get older, kicking in around adolescence in Gopnik's experiments, we switch to exploiting the strategies that we've already learned, rather than taking those risks. Children are also social learners. As well as interacting with their environment, they learn from others. Anyone who's ever had to deal with a toddler endlessly using that favourite word, why, will recognise this as a feature of how children learn. And they're very good at imitating other people, as you'll know if you've ever played with a child or talked to them as they learn to speak. What's more though, children of a certain age develop a theory of mind. In other words, they start to understand that other people aren't omniscient, they don't know everything, but they're actually other humans limited by the same constraints that limit them. And once you have a theory of mind and you know how your mind works, you can think about how other people's minds might work as well. This has been demonstrated in many famous experiments throughout the years. For example, the experimenter will sometimes hide an object from a third person without them seeing where it's hidden, and then ask the child, where do you think they think that the object is? At a certain age, children realise which knowledge is and isn't possessed by the third party. And this is also a form of reasoning and of empathy, learning something by putting yourself in someone's shoes and considering the knowledge that they must have had at the time. One fascinating aspect that arose from Gopnik's experiments is that you can influence how children will approach a task based on how you behave. In the experiment with toys, where different strategies could make the toy light up and make music, the kids were strongly influenced by how the experimenter behaved. If the experimenter behaved authoritatively, like a teacher, as if explaining precisely how the device worked, then the children were far more likely to copy one of the teacher's strategies. But if the experimenter behaved confused, acted if they needed help, and even acted surprised when they succeeded as if they weren't expecting it, then the child's creativity came into play, and they would actually go ahead and invent better strategies. This is even true when the kids are actually being shown precisely the same information. You can influence the approach that they adopt just by your sort of mannerisms towards them. And I think this really makes sense, of course. I mean, we work in the same way as adults in a lot of ways. If someone is showing you something and appears to be an expert, you go into receiving information and copying mode rather than inventive, exploratory, devising new strategies mode. If someone seems to be in control and seems to know what they're doing, then you're probably more likely to leave it to them or do what they do rather than necessarily coming up with your own strategy, questioning the wisdom of what they're doing and so on. But of course this does have some interesting possible implications for how we could consider educating children. I mean, we don't want to suppress this innate creativity, and yet at the same time it's also very difficult to see how you can get away from the kind of hierarchy of students and teachers in the current education system. A lot of these concepts taken from how children work and learn are already being imitated in machine learning algorithms. One example is the idea of temperature for algorithms. These are particularly in the case of searching algorithms that look through possible solutions to a problem to find the best solution. So, what do we mean by temperature in search? Well, you can sort of imagine a particle with high temperature, high energy, that's bouncing around really rapidly, versus a particle with low temperature, low energy that's just sort of slowly vibrating back and forth. A high temperature search is more radical, it's more wild, it moves around more quickly. It's more likely to pick a random move that might initially take you further away from the reward. Now this means that the optimization is less likely to get stuck on a particular solution that's hard to improve upon, but may not be the best one out there. But it's also slower to converge towards a solution. So one way to imagine this is what scientists would call a potential well, but what most people would just call a series of hills and valleys. Imagine you have a little valley, and then a small hill, and then a much deeper valley next to it. If you're getting stuck in that small valley, that's what we would call a local minimum. So you might bounce around in that small valley for a while, realising that you can get closer and closer to the ground where you want to go by heading down the hill. But if you were a high temperature searcher, then you might think, what's over the top of this hill? I know that it's taking me further away from the ground where I want to go, but I can see, in fact, there's a much, much better solution down here, and I can get right down to sea level if I take this valley. So that's the difference between a high temperature and a low temperature search. Searches with lower temperature will take fewer risky and random moves, and instead they sort of seek to refine what's already been found and discovered. In many ways, humans develop in the same way. From high-temperature toddlers who bounce around, playing with new ideas and new solutions, even when they seem strange, to these low-temperature adults who take fewer risks, are more methodical, maybe better at achieving particular goals and staying focused on a single task, but also far less creative. And this is how we try to program our machine learning algorithms to behave as well. This is something called annealed searching, where the search temperature cools down over time. And basically what you're saying is that your search starts by jittering around, going randomly through a whole set of different possible options, and then gradually, once it's found one that looks fairly good, it starts to iterate down and it starts to gradually, slowly move towards the bottom of that hill to create the perfect solution, at least of the solutions that it's found. It's nearly 70 years since Turing first suggested that we could create a general intelligence by simulating the mind of a child. The children he looked to for inspiration in 1950 are all knocking on the door of old age today. Yet for all that machine learning and child psychology has developed over the years, there's still a great deal that we don't understand about how children can be such flexible, adaptive and effective learners. In many ways, this sets up our own explore-exploit paradigm for machine learners and people who want to develop better algorithms. How much time do we spend looking at improving the existing strategies towards machine learning? And how much time do we spend observing things like observing children, looking into child psychology, looking into different types of design and so on, trying to find some radically new approach that will actually succeed far, far better once it's perfected than anything that we have today? It's difficult, and I don't think anyone out there has the answers at the moment. But understanding the learning process in minds of children, it will help us to build better algorithms, but it will also help us to teach, nurture, and help better and happier humans. And ultimately, isn't making a world where humans can be better and happier what technological progress is supposed to be about? Thank you for listening to this episode of Physical Attraction. The talk that this was inspired by was by Professor Alison Gopnik at Berkeley Labs, and it was at ICML. You can find the video online if you look on Facebook. It's a little bit difficult to track down, but she's given TED Talks and has books on similar topics, so it's worth seeking out those if you're interested. This show is available online at www.physicspodcast.com, where you'll also find the contact form that goes straight to my email. I think hopefully people will say that I'm usually pretty good at replying to those, and if you have any comments, questions, concerns about the show, episodes you'd like to hear in the future, do let me know about that. You can also contact us on Twitter at PhysicsPod and the Facebook page Physical Attraction. One of the best things you can do to help us is to donate to the show on the website by going through to the website and clicking on the PayPal link or the Patreon link. But if you don't want to part with your money, that's fair enough. Another thing that can really help the show is to tell as many friends as possible about it, or leave us a review on a podcasting platform. All of these things, help more people to find the show and hopefully help me to make the show better. Okay, we'll be back next week. Until then, take care.